Hello, everyone. Welcome to the first lecture for this summer Networks 2 course. Yeah, as you're aware of what's been happening, this course is going to be carried out online through online lectures, and that will be similar to what we did last semester. For about half the semester, I would say, we had to switch to online lecturing, and this summer semester is going to follow in this vein. Um, Different instructors opted to do different things. What I opted to do is I opted to move towards an asynchronous mode of lecturing where I record lectures and upload them on YouTube and then link them through Canvas, right? So that you can follow the lectures through YouTube. But then to offer some avenue for feedback from the students, I will open up a discussion thread that's associated with every lecture, so that if anyone has any questions or any points to bring up, they could bring them up in the discussion thread. Okay, and it should be like an interactive thing where I could reply directly to the discussion thread, so that the questions and my replies would be public to everyone. Okay, having said that, I will still maintain some sort of office hours, so to speak, virtual office hours. So what I'm thinking of doing is the following. I'm gonna set up a certain amount of time, perhaps 3 hours a week, where I log into Zoom, and I can then share my meeting details on Canvas, and anyone within those certain time windows, if they want to log in into Zoom, and more than one student is allowed to do that. So let's say I put in the Zoom login information or the Zoom meeting information, and then 5 students decide to join the office hours. That's fine. I mean, I think of it as similar to multiple students showing up at my office at the same time and listening while I'm having a discussion with other students. Okay, so I'm gonna try to maintain that office hour thing. So please stay tuned to the syllabus. I'm gonna edit it with the Zoom meeting information. Okay, so this course. Okay, let's step back a bit. This course is ECGR 2112, Networks Theory 2. My name is Ihab Shobeki, Dr. Ihab Shobeki. In real life, my office is 1165. It's on the first floor of the EPIC building, right? But since we are in an alternate timeline, we will be doing things virtually. I will rarely be there in the office, and I would recommend that. I would actually not recommend, actually, I would actually implore you not to show up at the office. Let's do this exercise of trying to do everything remotely, and I think it's pretty a reasonable thing to do. We do have the technology tools that would allow us to do that. Although the tools might hiccup sometimes, but most of the time they were fine. I mean, last semester was okay, more or less, and hopefully this semester uh, we will uh, we will have. Hopefully, I mean, me at least, I would have. I think I learned a lot from the hiccups that we went through in the last semester. Okay, right. So those are the office hours. Stay tuned. I'm gonna post specific office hours. I'm thinking right now perhaps 3 hours per week, and we'll do it through Zoom. So anyone is once I post the details about the Zoom meetings, anyone is welcome to, with questions, of course. If they have questions or if they just want to chat, or they have concerns, they can log into the Zoom meetings at the predefined times with their questions. The lecturing itself is going to be asynchronous, meaning that I'm going to record lectures on my Surface using OneNote, um, and then I'm going to upload them to YouTube and link them to Canvas. The I mean, if this was a normal semester, the lectures would have been Monday, Tuesday, Wednesday, Thursday. So on every one of those days, expect me to upload a lecture. Not at a set time. I won't commit to a set time, so I will just make it asynchronous, meaning sometimes the lectures might arrive 5 p.m. Sometimes the lectures might arrive 6 p.m. Right? There is no set time to uploading those lectures. Okay, that's what asynchronous means. All right. The textbook that we're going to use is going to be Basic Engineering Circuit Analysis by Irwin and Nelms, 11th edition or later. I don't know how you get it. If you want to get an electronic version, that's fine. If you want to get a hard copy version, that's fine. I'm going to mostly be following that textbook. I mean, the lectures notes would be the supreme. The lectures themselves will be the supreme guidance on what the material is that we're going through, right? So, luckily, since we are switching to online format, the lectures themselves are easier to get. It's easier for you to have a record of the lectures themselves. So for you to go back to at any time you want, right? So lectures come first, and then the textbook is going to be the reference, our reference. It will be our guideline as far as the topics that we are going to cover in this class. Well, as far as what topics are we going to cover in this class. Okay. My policy on grading is the following. I believe in homework, so I'm going to try to give you almost one homework a week. And homework will be like 30% or 30 points of the total grade. So that's number one. If you please solve the homework and submit the homework through Canvas. That's very important. I've encountered a lot of students who kind of did badly in the exams and then somehow did better in the final. But then because they were careless about the homework, that was not enough. Their grade did not get a good enough boost to get them to pass the class. Okay, so please don't underestimate the homework. That's a whole 30 points of your final grade. Okay, so please be mindful of attempting to do the homework and submit it. Even if it's not perfect at the beginning, everyone goes through a learning process. I'd rather you submit an imperfect homework than ignoring the homework. Okay, the grades are going to be classical A to F grades, and my philosophy is that your grade by itself does not matter much as your grade with respect to your cohort, to your group. Like if you get an 80, but the whole class got a 90 and above, that doesn't, an 80 by itself doesn't mean you did well. What matters is your position in class. But having said that, there is a minimum grade, letter grade that I'm going to give depending on your grade range. So if you look at the second page, and this is traditional, I mean, if your grade range is from 90 to 100, I'm going to give you an A. Right? I might, even if you get less than 90, you might still get an A. Let's say for some reason your group, like this class is a cohort of 40 people. For some reason, the whole class couldn't get more than 85. Right? I would still get the top grades. Like I would get the top earner, the top grade earner, an A still. Right? So those are the minimum letter grades. If you get an 80, that doesn't mean you necessarily get a B, but the minimum grade you're gonna get is a B. You might still get an A. Okay. If everyone does well in the class, then probably those grade ranges will apply. Of course, if you get less than 60, you're gonna get an F. Typically, I try to be lenient there, so where if someone gets a 59 or a 58 or a 57 or even sometimes a 55, I try to push them towards a D, but don't get, if you get a 40 don't expect me to try to push you. I will not. Okay, it is possible for people to fail this class. So please do your due diligence and you do your work. Okay. So this is the grading policy. Lecture sessions, textbook, office hours. What else do we need to discuss before we go to the tentative schedule? Yeah, I believe that's it. Oh, as far as the midterms and the final are concerned, I'm gonna do take-home exams for those, right? And it's important for all those take-home exams. It's important that you do individual work, right? So I'm gonna be careful with the exams. I won't give you questions that you can easily find online, but I expect you. The expectation is that you will do individual work. Right? If I don't want to see answer sheets submitted on Canvas where I see multiple students making the same mistake. Right? If everyone answers the same question incorrectly in the same way, that seems to be an indication that people are copying each other. Right? I don't want to see that at all. Be careful with that. I will give everyone a 0 who does that. Okay, so that's as far as grading is concerned. The tentative schedule is as follows. So this is called Networks 2, Networks Theory 2. In other universities, it would be called Circuits 2. It's a classical, traditional staple of the electrical engineering undergraduate syllabus. Typically you start with physics 1, physics 2, and then you do some bunch of mathematics classes. You do calculus 1, calculus 2, calculus 3, and then you might do a differential equation class. I believe in this university you have math 2171 differential equations, which is a prerequisite for this class, right? And then you do the physics 2. You finish the physics classes, which is physics 2102, right? And then after you finish those two classes and you finish the circuits 1 course, which introduces you to the introductory concepts of circuit analysis, you are then ready for this course. And since all of you are registered for this course, I'm assuming you are ready. You know your differential equations, you know your circuits 1, you know your nodal analysis, mesh analysis. You can analyze DC circuits. You encountered first order circuits, right? And then you encountered the physics concepts, physics 1 and physics 2. Okay, not that we will be heavy on the physics. This is mostly more on the mathematics. Circuit analysis tends to be. It derives some basic principles from the physics like KVL and KCL, but once you get to that starting point, all the analysis now becomes mathematical. Okay, and you've seen that with mesh analysis and nodal analysis and all of that. Okay, so this is like a typical course you would see everywhere, and the typical material that's covered in this course is going to be as follows. So we have our schedule is going to include 43 lectures, which is the expected amount of lectures for a 3-credit-hour course. I expect every lecture to be close to 1 hour, 50 minutes to 1 hour, and then I think on Banner they have set the lecture as 2 hours. I think that's a mistake, but I'll double check, because typically when you have 43 lectures in a semester, the 3-credit-hour equivalent is 1 hour per lecture. But I will double check that nevertheless. Okay. All right. So we should start today with this overview of the course, and then I'm going to start with an introduction about complex numbers. We want to review complex numbers a bit because we're going to use them heavily in this course. And then the next lecture is going to be introduction on operations with complex numbers. We'll finish our review in 3 lectures, so it shouldn't take more than 2, hopefully, right? And then the next topic is going to be second order transient circuits. I'm going to start it with a review of first order circuits, which I think you've covered in Networks 1, right? So I'm going to start with a review of first order circuits, then we will jump into second order circuits, explain what those are, explain the characteristic equation, and explain the response of second order circuits. As always, we will always, at the end of every section, dedicate a lecture for solving examples. Just like a calculus course, this course is going to be heavily driven by problem solving. You cannot claim to yourself that you understand the course unless you, or understand the material, unless you can solve problems in the materials. That's why I recommend that you, whatever ACTS version of the textbook you can get, I recommend you get that as soon as possible, so that you can solve problems on your own. When I give you homeworks, I'm going to give you the statement of the homework in the homework sheet. So you don't need the textbook for that. But I still highly recommend you to get the textbook, because I'm going to assign reading material. So I'm going to add to the schedule another column that has suggested reading. So for every section, there's a certain range of the textbook that you need to read. I highly recommend you do that so that you come to the lectures prepared. And then you need to solve problems on your own, problems beyond the problems that I give you as homework, right? You need to do that to ensure that you understand the material properly. Okay. The first homework I'm gonna give you sometime this week, and it's gonna be due on the 26th of May, right? And I'm trying to have homework due every 5 lectures, about every 5 lectures. So at lecture 5, you have a homework due. At lecture 10, you have a homework due. At lecture 15, you have a homework due, so on and so forth. We end up with around 8 homeworks through the semester. Okay. All right. So that will be this next topic. The third topic is going to be AC steady state analysis. Right. So you for all of circuits 1, you've covered a lot of techniques that were limited to DC circuit analysis, maybe meaning that your voltage sources, your current sources were constant, and you were trying to find the currents and voltages across the circuit, right, for constant sources. What happens if the sources themselves are varying in time, right? This is something we need to study to understand how to do. And one thing we can do is we can assume that those sources are changing with time steadily in a uniform manner with a fixed frequency. If we can solve that problem, it becomes easier to solve the general problem, which is sources that vary by any amount, that are a function of time, that vary by any way possible. The most general time varying sources, right? But we're going to start with sinusoids because it turns out that solving the problem for sinusoids, if we can describe the behavior of circuits for sinusoids, we can describe the behavior of circuits in general, right? And this comes from the linearity of circuits. We will describe that in detail when we get there. After that, midterm 1 will come. It's going to be a take-home exam over a whole day. I'm going to give it to you like around maybe midnight the day before, and it was going to be due midnight the next day. Right? And then after that, we're going to go to steady-state power analysis. Okay, so we have to understand how to analyze power for circuits that are driven by AC sources. The next topic will be magnetically coupled networks. We will discuss the ideal transformer, mutual inductance. Right. Up to now, the only magnetic circuit that you understand is the inductor, right? And but it's possible to connect inductors together, to link them together, uh, uh, um, couple them magnetically, so to speak, right? And that gives us the phenomena of mutual inductance or mutual coupling. So we study this phenomena in detail and how it applies to circuit analysis in those lectures when we study this section. And then after that, we're going to do an introduction on polyphase circuits. As you know, power transmission is dominantly three-phase. It's not single phase, right? So we need to understand what do polyphase circuits mean, right? Then after that, we're going to talk about the frequency response, right? So we started with AC analysis, where we analyze circuits with sources that are running at a certain fixed frequency. Then we need to understand how do the circuits respond to variation in the frequency. That's frequency response, right? That will become clearer as we get there. And then we're going to do midterm 2. And then finally, we want to solve the general problem. We want to know how to analyze circuits for inputs, sources that are any function of time. They're not sinusoids. They're not just AC signals. They could be any time signal, right? So how do we solve this general problem? The greatest tool that allows us to solve this general problem is the Laplace transform, right? Laplace and Fourier transform. The Fourier transform is a special case of the Laplace transform, right? Well, it's a matter of perspective. Some people would classify the Fourier transform to be the general case. So it's a matter of perspective, but I tend to think of the Fourier transform as being the special case. Because if you understand the Laplace transform, you understand the Fourier transform. So Laplace transform is going to be the tool for solving circuits in general, and that will be the final topic that we will cover in this lecture. It's going to take up a bunch of lectures. It's going to take up lectures from 33 up to 43, about 10 lectures. But it's well worth it, and it's a very useful tool for you to have under your belt. All right, so having gone through the schedule, let us commence with the lecture proper. All right. All right, so switching to OneNote, we're gonna start our course proper now. So, what are complex numbers, and why are they important for the study of this material? Right. Complex numbers are an extension of the real number system. So you have the real numbers, and we add something to the real numbers to give us, so we add something, we add extra elements to the real numbers, and that gives us the complex numbers, which, by the way, are called complex numbers due to historical reasons. They are called different things. They are called imaginary numbers. Imaginary numbers. They are called complex numbers. Someone like Gauss, the famous mathematician Gauss, didn't like any of those terms. He preferred to call them lateral numbers, because in many ways they are real mathematical objects. There is nothing imaginary about them. They are just an extension of the real number system. Why would we want to extend the real number system? Because it is useful, because it makes solving problems easier. That's the sole case for introducing complex numbers. They make, in our domain of study, in this case, which is circuit analysis, they make solving problems easier. They make understanding phenomena easier, analyzing electrical phenomena easier. If they make things harder, they would be useless. We're not introducing them just for their sake, their own sake, you know. Now the question is that you need to ask yourself, are they necessary? Like, can we work out a theory for circuits that does not depend on complex numbers? Like, can we work with circuits, right? Can we work with just signals that are let's say voltage and current signals that are just function of time and that are all real, meaning they don't depend on complex numbers at all? Yeah, we can, and we can build different differential equations from circuits and then solve them all without depending on complex numbers at all, right? So the complex numbers are, at least as electrical engineering is concerned, are not necessary, right? But they are useful. They are, although they are not absolutely necessary, we can still solve a lot of problems. Most problems we can solve without them. It is easier to do them than not to use them. It's kind of like the analogy here is a screwdriver. You could have electrical screwdriver, right? It's not necessary to use an electrical screwdriver to drive in screws. I mean, you could use a handheld screwdriver; it will work, right? It's not absolutely necessary to use a mechanized screwdriver, but it does make your job easier. So in a similar manner, complex numbers are not necessary, but they do make the job way easier. Uh, there are fields in science where they are necessary, where we cannot even start without them. And one big example is, I guess the biggest example is quantum mechanics. If you ever study physics and you study quantum mechanics, you find that you cannot even describe quantum mechanics without the concept of complex numbers. Okay. All right. So they do make the description of the theory underlying circuits much easier to use, right? And so what are they really? I mean, they are introduced as this extra number I. So you have your set of real numbers, right? So you have the real numbers. You have 1, 2, 3.5, pi, 2 pi. You know, you have e. You have a bucket of numbers, and then you add an extra number to those numbers, I. This weird number called I. Typically in mathematics they use I, but because in electrical engineering we mostly use I for current, so that we don't confuse ourselves. In electrical engineering, instead of using I, we use J to represent the imaginary complex number. Right? So from now on, I won't say I will say J. My personal preference is I, of course, because I mean it's easy for me not to confuse it with current, right? But let's stick to J because that's typical in electrical engineering. Right? But don't be surprised when you see literature out there that describes the imaginary value, the imaginary number as being I. Uh, 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 don't be surprised by that. That's how it was originally formulated. Okay. But in engineering we use J. So this is an extra number. This is an extension. So we have the real numbers and we just added something to them. And this addition has the property that J squared equals minus 1. This is a special kind of number where if you square it, you get a minus 1. On the surface, this does not make any sense at all, right? Because we know that that's why this number cannot be any real number, right? Because we know if we have two positive numbers and we multiply them together, we get a positive number. We have two negative numbers, we multiply them together, we get a positive number. There is not a single number, real number, that if we multiply it with itself, we get minus 1. Right? That does not exist because if the number could either be positive or negative. It's positive when we multiply a number by itself, that's positive, we get positive. When we multiply a number by itself, that's negative, we get positive again. So this number does not exist. This J number, I or J, does not exist in the bucket or the set of the real numbers. It's something that we tagged on. It's something extra, and it has that property. And this something extra allows us to define a bigger set of numbers, right? Where we don't just have 1, 2, 3.5, pi. We could have something like complex numbers, right? We could have combinations of j. So we could have j, we could have 2j, we could have 3j, we could have 5 plus 6j, so on and so forth. Okay. So this is the right. So this is the set of complex numbers. Okay. And this sort of extension where we take the basic number system and we extend it somehow is not alien, really. It's not something that started with complex numbers. This is something that I mean started from day one in the development of the number system. Right? This is something that's not, if you think about it, is not that weird, really. There's nothing mystical about it, and I'll show you why. Um, in general, whatever number system we work with, the basic thing we need to understand is a number system needs to obey a set of properties for it to be useful. And this is something we deduce from experience, from playing with this number system, trying to use this number system to solve problems, right? So what are those properties? Well, what are the basic properties of any number system, right? Any system where we're using something to describe quantities, right? Right, and if we understand the number system from that perspective, we can understand how we can extend any number system in a way, if we extend any number system in a way such that we meet those properties, basic properties, we should still be good, and the number system should still make sense, right? So any number system describing quantities, for it to make sense, really, it has to meet some properties, right? And those properties might sound trivial, but I mean they're good to keep in mind. So those properties are that the numbers need to be commutative. What does that mean? Well, it means that commutative under addition, right? Means that like 3 plus 5 equals 5 plus 3. That's a very basic property, right? Right? If I give a kid uh, 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 2 apples and then I give him 3 apples, he'll have 5 apples. If I give another kid 3 apples first and then I give him 2 apples, he should get the same amount of apples, which is 5. The order in which I give, right? If it mattered, like the order, when, like, let's say I'm paying for something. If I pay you $2 first and then I pay you $10, you get more money somehow than if I paid you $10 first and then I paid you $2. That doesn't make sense for this to be useful as a system for describing quantities. It's a very basic property where the order of addition should not matter. So this is called commutativity, and whatever number system, whether basic or extended, needs to meet that property. The second property is for it to be associative over addition, right? So if I say 1 plus 2 plus 3, the order where I carry this operation does not matter. So if I do 1 plus 2 first and then plus 3, or I do 1 plus 2 plus 3 first and then add 1. It should not matter. So this is the first important property, second important property. And then the third important property, which is going to be the key property that we're going to utilize when we extend number systems to complex numbers and beyond, is distributive property, right? And mainly distribution of multiplication over addition, right? So if I have 5 times 3 plus 7, I can distribute the multiplication over the addition, and I end up 5 times 3 plus 5 times 7. That's also a basic property for a number system for it to make sense. Any system that is used to describe quantities. Okay, and I said there is nothing weird about taking a number system that meets those qualifications, those properties, and extending it. It's something that naturally occurred throughout history, and it's not something that became suddenly bizarre when we introduced complex numbers. It looks bizarre because when we think with ourselves, we can understand what it means to have 5 apples. But it's kind of perplexing to think, what does it mean to have J apples, right? Because this doesn't make sense because we are thinking about this in the wrong context. Okay, so let me say what I mean. Okay, so first I said this idea of extending a number system is not that bizarre, because naturally, I mean, we started as humans, we started with very basic set of numbers first, right? We started with the natural numbers. So we started with 1, 2, 3, 4, up to I don't know. It goes on and on and on and on. The joke goes that originally humans could not count more than 3. So it'll be like 1, 2, 3, and then many. Right? But eventually we got to that concept of, hey, I mean, we can count as high as you want to count. We understand the concept of numbers. Yeah, 3. There's something about 3 elephants, or and 3 people, right? Is that kind of like, or 3 elephants and 3 loaves of bread? I mean, 3 elephants and 3 loaves of bread are totally different things. But there is some abstract notion in which there is sameness there. It's like the same amount of things. Okay, and we early on in our history understood this abstract concept of counting. So natural numbers come from counting, right? But we didn't just stop there, right? It took a while, but then slowly we started to recognize that we need to add something that represents nothing. And this is something that we take for granted now, but actually it took people a very long time to accept the concept of 0, right? Accept the concept of a number that indicates nothing. Actually, it took us way more time to accept the concept of 0 than it took us to accept the concept of complex numbers. Right? That's how radical the idea of 0 was. So now our number system has 0 added to it. 0, 1, 2, 3. Right? This is called what? The integers, right? Okay. So now we have a different number system where we have an added element. It is still a valid number system. Why? Because those basic properties of arithmetic, of quantities, still apply. It's still commutative to addition, so it still makes sense. It's still associated with addition. It's still distributive with respect to multiplication. Right? We know that 0 times any number is 0. Okay. So that's great and all. I mean, people could use these numbers to solve problems, solve equations. Let's say x plus 4 equals 5. What should x be? We know that x should be 1, right? So you encounter problems in life where you need to solve an equation, and you use those numbers to solve those equations, right? You use those numbers to get the solutions. But then people started encountering, once they were dealing with money, for example, they started encountering problems where you might owe someone money, but someone might owe you money. So there was a sense where there has to be a sign associated with numbers. Meaning, if I encounter an equation, so an equation like x plus 4 equals 5, I could solve easily with my established number system of the integers. What if I have a problem of x plus 4 equals 2? Can I solve this with respect to z number system? No, I cannot, because the solution needs to be something that we know now to be minus 2. We understand now the concept of negative integers. We understand that those are the positive integers. We understand that numbers, not only 0 exists, numbers smaller than 0 exist. So this is another extension of the number system, right, where we introduce negative integers. So it goes from minus infinity, minus 5, minus 4, all the way to 0, and then 1, 2, 3, blah, blah, blah. Right? So we introduce the concept of negative integers that seemed fantastical to people at the time. It also took the people long time to accept negative integers. It took them less than time to accept them than to accept 0, but it still took them a lot of time to accept them. Right? But they are very useful numbers because they can be used to solve equations such are those, right? Right? If and they're very useful in describing depth. So you could quantities could be positive or negative. I could have some money in my bank account if I'm dealing with money, and people at the time historically started dealing more and more with money transactions, and then I could be in debt to someone, so I have like a negative account. So the concept is very useful in describing real life situations, real life. It has real life applications. It wasn't just some abstract thing that the mathematicians added. Hey, let's have fun and let's just add negative numbers. Right? It still was like kind of it still kind of was like a mind trip for people to accept them, but people got to accept them and people got to recognize their usefulness. Okay. Uh, uh, um, Of course, beyond that, beyond the integers, you might have equations where like this, like x plus 4 equals 1, 5x plus 4 equals 1. To solve this equation, you know that x needs to be, uh, 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 right? What does x need to be? X needs to be minus 3 over 5, right? So here again is a practical problem that arises. And this is an equation that could very well arise from a practical problem that you're trying to solve, where it turns out, hey, that your number system is still not adequate. We still need a bigger number system to solve problems adequately in real life. And the bigger number system here involves rational numbers. So if we imagine numbers as being segments on a line, so this is 1, this is a quantity 1, right? It's a segment on a line. This is a line. I can imagine that I'm divvying up the line. So I can divvy up the line into 3 portions, and each portion is 1 over 3. Right? So this concept of dividing integers together to get rational numbers, right? The idea is that 1 over 3 times 3 equals 1 unit. So this concept of divvying up units of number to get fractional numbers is called the rational number system. Right? And this is the other big extension then to the number system. Actually, the rational number extension came way before 0 and way before negative numbers. It came first, then 0 and negative numbers came. But when we add this extension to the number system, we get Q, the rational sum numbers, where we have any numbers such that as 5 over 4. I'm gonna write them not in order. Minus 3 over 2, blah blah blah, 1, right? Because 2 integers are still rational numbers because you can write 2 as 2 over 1, right? 5, whatever. So it's a set 22 over 7. This is an approximation of pi, right? So this is a bigger set. This is so we started with the natural numbers. We extended it with 0 to get to the positive integers. We extended it. This is an extension, right? To get all the set of integers, positive and negative, we extended it to get the rational numbers. Okay. That's still not complete, by the way, because there turns out there are certain numbers when we studied geometry, when the Greeks studied geometry, it turns out there are certain kinds of numbers that you cannot describe as any rational number. For example, if you have a triangle and you have 1, 1, square root of 2, okay? The hypotenuse is going to be square root of 2. It's going to be 1 squared plus 1 squared square root, right? So the Greeks for a long time thought that rational numbers are all there is. They didn't know much about negative numbers, of course. They didn't know negative numbers are 0, but they thought that rational numbers are all there is. You don't need any more detail. I mean, take any unit, divide it into any amount of units you want, right? And then you can describe any quantity. So the Greeks thought that, hey, this triangle is square root of 2. This is a radical. This is called taking a radical. They thought, hey, if they worked hard enough, they could write square root of 2 as some rational number. They could write it as some, I don't know, 7725 over 5437, right? It's a hard problem, but they thought that if they put their minds to it, any number that can be described like this in geometry, like square root of 2, that naturally arises from geometry, from Pythagoras' theorem, they can describe any number as a rational number. It turns out no, and this is a famous story. I encourage you to read about it. The story is that there was a guy who proved that this is not true. I cannot describe square root of 2 as any rational number. There's no way to describe square root of 2 or square root of 3 or any radical really as a rational number. Those kind of numbers are not rational numbers. They are not rational numbers. And the famous story, perhaps it's not true, it goes that the guy who proved this, I encourage you to look up his proof, it's a very interesting and elegant proof, was thrown out of the boat because he disrupted and drowned actually because he disrupted the fairy tale world that those people who followed Pythagoras at the time used to have, that numbers are very orderly and very and really everything exists within the rational number system. Okay. So it turns out, no, there is a bigger set of numbers, which is called the real number system. And this is the number system that you are familiar with from calculus, right? So this is the number system that has all the integers, right? 1, 2, 3, minus 4, whatever, 0. It has all the rational numbers, 5 over 4, minus 7 over 3. And it has all the irrational numbers, numbers that cannot be described as a rational number, like square root of 2, square root of 3. Another example that's not a radical is pi, for example. Pi is not a rational number, e, so on and so forth. Right? So this is the final extension before we go to complex numbers. Okay, so we went from natural, positive integers, rational numbers, real numbers, right? So the final jump to complex numbers is just one small jump compared to the trajectory that we went through since the beginning of history. It took thousands of years to go from the natural numbers to the real numbers. it took us maybe 100 years or so to convince ourselves of the validity of complex numbers. So it's not that bizarre as it seems to be. It's a very orderly process. Uh, um, right? So what are, I mean, I've presented this as, oh, by the way, all those extensions, as we extend the number system, doesn't matter how much detail we add to the number system, how much elements we add to it, how much more numbers, different kinds of numbers we add to it. The basic thing that needs to always remain true for any quantity to make sense is those three properties. It has to be commutative, associative, and distributive. That's all that matters. It doesn't matter that in your mind, J apples does not make sense. J as a number makes sense if it meets those three properties. That's it. Then it can be used. Anything you can concoct up or come up with that meets those three properties is a proper number, right? And just giving you a hint, complex numbers are not the end of the line. There are more elaborate numbers that are called hypercomplex numbers. Right? But those we will not use in electrical engineering. And in many ways, we are stopping at complex numbers. We're still very general and very useful, right? But they are all we need to study electrical engineering. So I posed this, by the way, I posed the need for extending the number system as something that arises from the need to solve a problem, real life problem. So you encounter a problem, right? It's like the problem is, it's like I have an X amount of money in the bank, in my balance. And if I add 4 to it, I end up with 2. What amount of money do I have in the bank? That's how people thought. Like there was a word problem, you turn it into an equation, right? And you use the number system to solve the equation, right? So up to real numbers, you can solve a lot of equations, problems that arise from real life. Where do complex numbers come in? Why are they useful? What solutions are they for? Right? They are solutions of equations of this kind. So equations, polynomial equations, which also arise in real life problems, right? Such as this, x squared minus 4 equals 0. You need to solve such polynomial equations, second order, let's say. So we can solve this easily. This is x equals square root of 4 equals 2. Square root of, 2. So x equals 2 or x equals minus 2. Because squaring could be, when you square minus 2, you get rid of the minus sign. Okay, so they have, quadratic equations have two solutions, right? But then there are some kind of equations that we encounter, such as this, x squared plus 1 equals 0. And people discovered that they cannot solve this kind of equation is not solvable in the real number system, right? Because it requires a number that when we square and plus 1 to it, it gives us 0. Such a number does not exist, right? So what people did is that and there are very deep historical reasons for people doing that. They had to do that. People in the beginning was like, hey, forget about it. We cannot solve those equations. Hey, consider those to be unsolvable equations, right? But in the history of the subject, it turned out that people actually were interested not in those sorts of equations. They were interested in quadratic cubic equations like x cubed plus bx squared plus cx equals 0, right? They were interested in those sorts of equations, and they found out that to solve those equations properly, they needed to solve some intermediate equations, quadratic equations of the above form, like x squared plus 1 equals 0. So to get to the solution of this, first they had to solve this so that they can solve this, right? But although this kind of equation doesn't have a real life solution, according to their understanding, it was still useful for them to solve this equation so that they can use the solution to solve the bigger equation that has real life applications. So it was kind of like a weird thing for them. It was like you want to solve a concrete problem, but then you have to do some magic in the middle. You have to assume that this problem has a solution so that you can solve the ultimate cubic equation. It's a very interesting history. Again, I would encourage you to read that history, right? But that kind of like sort of fictitious solutions that they called it. People thought it was nonsense on one hand, but then on the other hand, people were finding that they are getting correct solutions for the cubic problem if they think that this has a solution, this equation has a solution. So it was nonsense on one hand, they thought it was nonsense, but it was giving them useful results, right? So that slowly kind of like opened their mind to accept that those kind of equations have a solution. And that solution, although it does not exist in R, it exists in an extension of R. R, the real number system, and we add to it something. So I take R, and then I add to it something. And all I need to add to it is J. And this J is the special lateral number according to Gauss, or imaginary number, or complex number, is the number such that if I take I and square it, I get -1. Once I introduce this extra number, this becomes the solution to this equation. Right? The solution of x squared plus 1 equals 0. The solution is J, or minus J. Right? So by introducing complex numbers, we could solve any second order polynomial. Further than that, it turned out by extending, going from R to C, the complex set of complex numbers, we can now solve any polynomial. So any polynomial xn plus an minus 1, xn minus 1, an minus 2, xn minus 2, all the way to a 1x plus a 0. Any polynomial has n roots, and those n roots are in C, in the set of complex numbers, not in R. Right? So this is a very beautiful result, because previously people were like, hey, if I have an nth order polynomial, like if I have x squared plus 3x plus 1, there were a lot of special cases. Hey, sometimes this has two solutions, sometimes this has a solution, right? Sometimes it has no solution. Like there was a lot of special cases. Like if I have a third order equation polynomial, sometimes it has 3 solutions, sometimes it has 2 solutions, sometimes it has 1 solution, sometimes it has no solutions. Oh, by the way, third order, forget I said that. Third order would always have a minimum of 1 solution, right? But I mean, the point it was a lot of special cases. But when you have complex numbers as solutions, you end up with a very beautiful result that nth order polynomial is going to have n solutions. That's it. Simple. Fifth order equation is going to have polynomial will have 5 solutions. Those solutions might not all be real. Some of them will be complex, but nevertheless, it's a very easy, simple statement. They will have 5 solutions. Okay. Why is that? That's what complex numbers give you. Why is that important for engineering, electrical engineering? Why do we bother? Why didn't this just remain in mathematics? Right? Because polynomials arise when you solve equations. Okay? That's the point of engineering. What we do, we take the physics. That's what we do as engineers. And then we build a mathematical model This mathematical model is in the form of a differential equation, right? So we use our knowledge. We go to physics. Hey, we say that to the physicist, give us your results, your theories. We want to use them on this problem. I'm building something, or I'm analyzing something. I want to understand something in electrical systems. So I take the physics, I build the mathematical model, I get a differential equation. I want to solve this equation to get results, useful results that I can base my analysis on, or my design on, or whatever, right? And intermediate, if you remember your differential equations, an intermediate step in solving differential equation is getting the characteristic. A characteristic equation is a polynomial, right? So to solve differential equations, we need to solve polynomials. And solve and those polynomials give us, when we solve them, they give us information about the solution, or the response of the system, or the solution of the differential equation, right? But we said we cannot solve polynomials in general. Polynomials will not always have solutions unless we expand our number system from R to the C, to the complex number system. So that's where their use comes. They make it easier to solve differential equations because now they make the solution of the characteristic equation that arises from the differential equation very regular. We can simply describe it using complex numbers. Okay, so we're going to go through detail with that yet a bit. We're going to review it. I'm not going to depend fully on your memory of solving differential equations, right? But I wanted to give you like sort of the justification for installing in R. Why not just live in R and solve everything in R? Why do we have to go to this extended number system where we have R plus this extra number that we have? This is the reason, because when we solve differential equations, we get characteristic equations that are polynomials, and we said complex numbers make solving polynomials much easier, much more regular, right? A fifth order polynomial has 5 solutions in the complex number system. We don't have to worry about special cases where there is 1 solution or 2 solutions or 3 solutions. It will always have 5 solutions. Right? Plus complex numbers in many ways also make the form of the differential equation solutions easier. So it makes the form of the solution easier and more compact. And we see that. Okay. So yeah, this was a bit of I encourage you to read on the history of this. It's a very informative history. But all you need to know is that the complex number system is just the real number system with that extra number I, okay? And then it has to obey those 3 properties. And that allows you to understand everything about complex numbers. Okay? Now we have, yeah. So what does that mean? That means, hey, I have the complex number system now, which is R real numbers plus J. Right? That means for this to be like this is C. For this to be a valid number system, it needs to obey the properties, right? First, it needs to be any complex number I should add to any complex number, right? So C, this big bucket of complex numbers, has the reals, right? Or the integers. So it has 5.5. I should be able to take to this number and add it to any number and still get a number. So something like 5.5 plus J should also be a number, right? Because that's the basic property of numbers. It's called closure. You take any number, you add it to any other number, you get a number. You take any number, you multiply it by any other number, you get a number, right? So that means that although I added J as one extra element, I still have like a big set of different kinds of numbers, because I can always combine J with any real number to get also a number. So if I combine 5.5 with J, I should get a number. If I take J and multiply it by 6, I should also get a number. So 6J is a valid complex number. I could take 7 plus J times 8 plus 5j, and this is still a number, right? So I can generate any kind of enumeration of a complex number by just combining different complex numbers together and being mindful of the basic property that, hey, numbers have this basic property that I can add them together to get other numbers, I can multiply them together to get other numbers. The question is now, how do you do this multiplication, right? And here, to do this multiplication and addition properly, here you have to be mindful of the properties of commutativity, associativity, and distributivity of multiplication or addition. So let's start with addition. Addition is simple, right? So I have a general complex number, a plus the most general complex number is going to look like this, a plus jb, right? I can take j multiplied by a constant and then add it to some real number. That's a very general complex number. Let's say I add it to some other very general complex number, c plus j d, right? Using the properties of commutativity, I can move those constants around, right? And nothing will change. So I can move a towards c towards a. So I end up with a plus c. Using associativity, I could put brackets, right? It doesn't matter the order, right? And then plus jb plus jd. I could use distributivity. I could imagine that I could take j out. So I end up with b plus d. Right? This is another general complex number that seems to be the sum of those two complex numbers, 1 and 2. And I got there by just considering associativity, distributivity, and commutativity. Nothing more. There's nothing fancy about this. It just comes from considering those three properties. J could, due to distributivity of multiplication over addition, J should go into B and D, and I should still get the same number. Right? So this gives me the definition of addition. That if I have A plus JB plus C plus JD, the sum should equal A plus C plus JB plus D. Okay. What about multiplication? Okay. Again, I just use the three basic properties. I know if I multiply a number by a number, I need to get a number. So if I multiply a complex number by a complex number, I need to get a number. But then I can also, I know that I can apply distributivity of multiplication for addition, and it should apply in any valid number system. So I could, to define multiplication, I could consider A plus JB, C plus JD, and all I need to do is apply distributivity. I don't need to do anything fancy. So I can distribute A, I can distribute this whole thing inside the bracket, and then I can distribute again. So I can say this is equal to A plus JB. If this is a valid number system, it should equal this should equal the same as that. Right? So A plus JB times C plus A plus JB times JD. And then I apply distributivity again. I place C inside. So I end up with, let me remove the brackets. I end up with AC plus JBC plus I take DN. So I end up with JAD. Now here I have BD, but then I have J times J. We know what J times J is. J squared is minus 1. That's the basic definition of J. Right? That's what we defined J to be. So that tells me that when I take JDN, I end up with minus BD. And then due to commutativity, I can redistribute, move those parts around, components around, and I should still get the same number. So if I do that, I get the definition for addition. What is presented to you as a definition for addition. It's really not a definition at all. It is the result that arises naturally from obeying the basic properties of numbers. So I end up with AC minus BD plus I can take J out due to distributivity again. I end up with BC plus AD. And this is how multiplication works for complex numbers. So, and that's all you need. You have a general complex number, you add to it a general complex number, you end up with another general complex number. You have two general complex numbers, you multiply them together, you end up with a third general complex number obeying this form. Okay, and this is it. You know now how to manipulate complex numbers. Things don't end here, by the way, of course, because I mean, we could still work with this representation of complex numbers, but it sometimes is easier to alter, to represent complex numbers differently, right? So this is what I will talk about in the next lecture. I will talk about different representations of complex numbers. All right. Thank you, guys. See you tomorrow.